Thank you very much for giving me the opportunity to give this talk in front of you here. So what I'll talk about is the team that I have built in Denmark and how we have created a company from a university and how we have acquired customers in the private sector that are now buying our products. So just a little bit about my own background. So I'm a graduate of Oxford University in 1992, and ever since 1992 I have been feeling, thinking, and talking quantum the rest of my life. So it's in my blood. After I graduated from Oxford, I went to Berkeley, University of California, Berkeley, and after that I was hired at Harvard. But I really wanted to try to come home to Denmark. Sorry, is this not working? No. Is this working now? Is this working now? No, I just continue here. So I wanted to come back because there was really great opportunities to run a big center in Denmark and to get a lot of people to work together on specific problems. So I got one of the early investments in quantum in Denmark, which is from the Danish National Research Foundation. And I was studying at Aarhus, or working at Aarhus University at that time. But somehow that built the foundation for what I later did, at another quantum center that I built. Because I was able to get an ERC Synergy grant, which is the biggest grant you can get in Europe. And so getting that meant that I got a lot of offers from various places in Europe, in particular some of the universities mentioned at the top. But I chose University of Southern Denmark because they offered really a huge build-up around this activity. They offered a permanent center for quantum mathematics, and they offered the possibility to be adjoined to the Danish Institute of Advanced Study, and they offered a very special model for commercializing this, which I'll get to you in a second. So I'm also the director of the SDU Quantum Hub there. All right, so what we really do at this center is we are developing the mathematical foundation of quantum theory. So there is a perfect mathematical model for quantum mechanics, but for quantum field theory and string theory, there is no full mathematic theory that really works. You know, there is actually a Feynman path integral formulation of quantum field theory, but we can actually prove that these integrals don't exist mathematically. So there's something else has to be in this place, and we are developing this. But as a spin-off from this, we're developing new quantum algorithms and quantum software. So I've arranged an international advisory board. So there's no Nobel Prize in mathematics like there is in physics, but there are Fields medals, and there are 6 Fields medalists on the board. So we're really aiming for a very serious academic build-up in this field. And they have helped me hire a lot of very strong people from around the world. We are insisting on having an elite build-up so that we could be competitive at the absolute top in the world. And so if we go through them from over there, you see Vivek, the first guy, he's hired from Berkeley. Dupay, the second guy, he's hired from Harvard. Shan is hired from Duke. Fabian is hired from Oxford. I could continue this way. It's really a serious build-up. We are 50 now, so you only see about 30 on this slide, but there's actually 20 more, but we are accelerating quite fast, so we haven't updated the slide. I apologize for that. We have brought in quite a lot of research grants, and so by now we have about 40 million euro in research grants. They come from Europe, from ERC in particular, which is sort of the most prestigious one in Europe, but then also from the Simons Foundation in the US, and then from a number of different sources in Denmark where there are lots of possibilities. Many companies have foundations where they actually give money to science in Denmark. And so, for example, the Willem Foundation is such an example, the Carlsberg Foundation, which you might know, Carlsberg, and then the Novo Nordisk Foundation is another example. But then on top of that, the government has introduced a new quantum strategy, and so we've gotten some funds also from the Innovation Fund Denmark. We got 20% in the first quantum call, and actually 100% of what they gave to quantum software. Well, the quantum industrial revolution, I think everybody in this room here realizes this is now serious, and we need to act in relation to this. But the whole world realizes this too. You know, there are lots of people out there actually doing this. And so you have to find your own niche, but I want to note that we actually, in the fall, went to Japan, and so the woman in the picture here is the Prime Minister of Denmark, And she spearheaded a delegation to Japan to sign a collaboration agreement between Denmark and Japan. And I'm really hoping that we can get to the point where that could be possible between Denmark and Korea as well. But Denmark is really somehow building up very strongly on quantum. We have a long legacy. You know, quantum theory was basically invented by Max Planck. But we have a star in the field as well in Denmark called Niels Bohr. And, you know, he had his atomic model and so on. And so he was a big name in quantum as well. And he's Danish, and his legacy really somehow still stays on in Denmark. And one of the things that we now are going to do is actually enhance our education activities. So in particular, we are now developing a new education in quantum computing that we are hosting at my center at SDU in Denmark. So it was just approved by the ministry, and we will take in the first cohorts in 2025. And I hope you will send all your best graduate students, or actually finished bachelor students, to come and study with us. I can guarantee you that we will provide a very strong education where they won't just get the standard Q-gates, Q-bits education in quantum computing, but a really deep mathematical understanding of the subject and ability to think new and create new algorithms. So let me tell you a little bit about the details of what we do. At the Center for Quantum Mathematics, we are interacting with a lot of hardware producers, like, for example, Qurera, which is a Harvard-MIT spin-off. We are working a lot with Quantinuum, with IonQ, with Atom Computing, with Google, and with IBM, and with Xanadu on the photonics. And then I'll show you a few others that we are working with in Denmark only. So we are working together with the Danish Technical University, which is located in Copenhagen. We are developing photonic chips, also in collaboration with Xanadu. And what we're doing there is we are building a very special platform called Gaussian boson sampling. I'll get back to you about what that really is if you're not familiar with that quantum computing platform. We're also doing QKD, as you are doing very well here in Korea. We have a small proof of concept that's going on in Denmark, a network in Copenhagen, and a long link from Copenhagen to Odense. But it gives me a chance to show a little piece of the Danish geography so that you can see where Odense is in relation to Copenhagen. So there's only an hour and 10 minutes between Copenhagen and Odense by train, so it's very easy commute. And you live very nicely in Odense, and then you have all the amenities of a big city nearby. So it's very simple to live there. Just another commercial for Odense. So that I will skip entirely. If I just want to say a little bit about the latest project that we are doing, I have been working all my life on topological quantum field theory. And topological quantum field theory is the thing behind topological quantum computing. So the theory that I worked on has been known to be universal quantum computer for 20 years. But, you know, it was sort of not really interesting some time ago until all of a sudden the hardware started exploding, maybe in 2019 when Google showed its supremacy experiment. And so since that, we've really been somehow pouring a lot of resources into actually implementing the various TQFTs that I have been working on. And we're doing this also with Quantinuum. Some of you may have noticed that Quantinuum came out with something on topological quantum computing. They thought they had a universal theory in there. But one of my theorems actually shows that that theory they were implementing is not universal, but we've now told them which one they should implement to be universal. But together with people from DTU, we are actually implementing a very special TQFT that I invented 10 years ago. This is in the CV formalism as opposed to in the digital formulation of quantum computing. So that means we're talking about Q modes, and we're talking about unitary operators on infinite dimensional Hilbert spaces. But this TQFT has very special properties of being very inert towards errors. And so we're really looking forward to actually fully implementing this. And ideas from Gaussian boson sampling going into this, and I'm coming back to that in a second. So yeah, here's some of the work described in mathematical terms that I have been doing over time, way before any of us started really thinking seriously about doing quantum computing, except for few pioneers in quantum hardware some 20 years ago. But I won't go for the details of this. I think this is not the right sort of time to do that. But if you like, you can come and ask me what are the theorems that I proved in topological quantum field theory that are related to this topological quantum computing. But I want to tell you about a very special quantum computing platform, which is not so well known, but actually is super, super powerful. And it is actually easier to build than a full-fledged universal quantum computer. And so this is Gaussian boson sampling. And so Gaussian boson sampling is a bit similar to the Japanese game, which is very popular over Japan, called Pachinko. And what you have there is a steel ball that drops out at the top, and then it bounces off some steel rods that are sitting there, and then it falls into one of the brackets at the bottom, and you have to put your money on where it lands. I know this game is not legal here in this country, but I might assume that you know it anyway. But so this thing here you can do quantum mechanically also. What you do is you shoot in lasers at the top. Sorry, this doesn't work. I'm sorry. You shoot at laser beams at the top, and then those hit some squeezers, and then you have the output of the squeezers is squeezed light that goes into a set of unitary transformations, so passive optical components, squeezers, and phase shifters. And then at the very bottom, what you do is you do photon counts. And so now what you have to do is describe what is the probability distribution of photons. Oh, I'm sorry. What is the probability distribution of the photons that come out? And so that is mathematically very complicated to describe, but it's possible to understand completely. And it's actually proposed, a certain version of this called boson sampling, but it's very similar to this, by Aronson and Arkhipov. And what they proved was that unless the polynomial hierarchy collapses, this is impossible for a classical computer to simulate. And we can actually see by experiments that if you go to about 60 channels, the biggest computers in the world can't do it. There are some people out there who claim that they can go a little bit higher and so on. That's because they have tampered with the precision and they have tampered with exactly which examples they're looking at. So, but in general, it is really, really hard to do this. And nobody believes the polynomial hierarchy collapses. It's a fundamental assumption in computer science. It would mean that, for example, the traveling salesman problem could be done in a polynomial type. Nobody believes that is the case. But when they sort of wrote this paper, they wrote in the end of the introduction, gee, we wish that we had a very good practical application of this fantastic quantum computing machinery. And so that's actually what we have developed. So I'm going to skip the next few parts because I think I just want to try to get to the precise thing that we have done. So what you're looking at here is what we call a Gaussian weighted integral. So the function h is the Gaussian, and you see that it's a multivariable Gaussian, and that's determined by a quadratic term, which you have right here. And that quadratic term is determined by a symmetric matrix B. And that matrix you should think of as the covariance matrix between various things. It could, for example, be stocks, or it could be all kinds of different things. And now what you're doing is you're averaging a certain function that could, for example, be the payout function in an option, and you're averaging this over Rn. You want to compute this mu here. Now, this may look like a very special thing to do, right? It's just some piece of special mathematics. But I can tell you that any optimization problem you can think of can be reformulated as computing such an integral. So that means all kinds of optimization processes can be described this way. Also, any kind of financial derivative can be expressed this way. Also, any solution to a stochastic PDE can be described this way. So this is super, super versatile problem. It's notoriously heavy for a classical computer to do. I can tell you, for example, that every day when the bank closes in New York, 10% of the world HPC capacity starts working on trying to compute what is the risk that the bank has. And so it's running all night to compute for next morning, where are they in terms of risks? And all they're doing is computing these integrals. So that's an example of how, very concrete, right? And so the point about this is that what people normally do is they use Monte Carlo simulation to compute such integrals. But what we have been able to prove, and here I'm saying prove, so that's very important to note, we can prove that for under certain assumptions of this function and the matrix B, we have exponential speed up over Monte Carlo simulation. So there are 3 quantum algorithms already known to have exponential speed up. One of them is Shor's algorithm. I'm sure you all know that here. There are 2 others, but now we have 4. So we have one of the last ones here. So it's a very recent result. And if you look at the graphs at the bottom, you can see that the red line is GBS computation and the blue line is Monte Carlo simulation. And you can see in all 3 cases that it converges way faster using Gaussian boson sampling than it does Monte Carlo simulation. And so this is a completely universal tool now that we can use, and it makes this GBS very useful platform to work with. We have similar results for boson sampling. And boson sampling can be emulated on a standard qubits, Q-gates quantum computer. If you want to do Gaussian boson sampling, you have to employ CV formalism. So you have to do, quantum photonics, for example, or you have to work with bosonic modes, say vibranic modes of various atoms. But there are several platforms and a number of companies that do this. So for example, Xanadu is probably leading in the world on building Gaussian boson samplers. They have 216 channels for now. There's also Orca, which is an Oxford spin-off that builds these. So they are available. And so how can we use this somehow? And we believe that this is going to affect many different kinds of industries, because I do not know of an energy sector that does not optimize their production in some way or another. Okay, so let me just show you that the construction we have made in order to somehow make sure that this is useful for the industry in Denmark and beyond, of course, for the industry in the world. But we have started focusing on Denmark since we're based in Denmark, but we're very much looking forward to going into the Korean market. And so the way we have constructed things is that we have a spin-off company, which you see right there in the middle, which is called Qpurpose. And this company is a privately owned company, and so that can go into business-to-business contracts. So we have, for example, a business-to-business contract with Jyske Bank, which is one of the biggest banks in Denmark. That contract specifies precisely what kind of deliverables and service follow-ups, because they want a lot of service follow-up. This is something the university cannot hold, and therefore we have this construction. So when we have signed the contract with Jyske Bank, which we did about a year and a half ago, then we distill the research part of this project. That is then bought at the university, which is over here, where my center at the university is. So we buy on-contract research at the center. We pay 130% in overhead, but then all the intellectual property rights goes back to the company. And so we can sell it on to the industry partner, or we can sell it to the full industry sector, or whatever we wish to do. And so we have a number of different companies, as you can see. I can just very quickly go through them. So MSCI is the world's biggest investment decision support tool producer. They produce these tools for all the banks you know, all the Korean banks, all the American banks, and so on. And we are using these methods now and starting to implement that in the way that they run their optimization for these computations of these integrals. In terms of Jyske Bank, we're actually developing things that are running on their trading floor right now, and so it's being tested there. And as soon as this is tested and verified to run, then we will sell it to the sector. But we want to make sure that it's running completely perfectly and optimizes perfectly before we sell it to the rest of the sector. And then we're also working with the Danish energy sector, which is Ørsted. This is the biggest Danish energy producer. 60% of the Danish energy is produced by wind energy, and so that requires a lot of optimization, and that's what we do for them. Finally, we're also working on the energy net in Denmark, and we're working together with the Danish Meteorological Institute, and we're working with some of the biggest companies in terms of logistics. So Maersk, you see up in the corner, that's the biggest shipping company in the world. It's Danish. And then, of course, the biggest pharmaceutical company in Europe, that's Novo Nordisk from Denmark also. We're doing various things like optimizing ligand docking to proteins for them and other kinds of pharmacological things and, market optimization and so on. All right, we believe this is applicable to all industries, and we are very open to collaborations with any kind of branches of industry in Korea who might wish to work together with us. We have met a lot of interest here, and so that's very exciting. And so I just want to end by saying thank you very much for your attention.
예, 감사합니다. Any comment or question? 예.
Maybe a very specific question, but you mentioned this to can also be solved by this
Boson samplings. Would you just comment or just elaborate?
Yeah. The reason for this was developed about 25 years ago when people in the financial sector was very interested in trying to understand PDEs and how they modeled the market. And what they discovered was that there is actually path integral formulations of solutions to these PDEs. But they couldn't really solve them because, okay, they reformulated into something that then they couldn't compute because path integrals are very notoriously difficult to compute. But we have developed a way where we can do weak rotation of the covariance matrices in such a way that they become complex. And then what happens is that the path integrals are path integrals for quantum mechanical processes that follows the Schrödinger equation evolution. And therefore, we can actually solve them on quantum computers. But if I also want to answer the question in relation to GBS, the point is that these path integrals are infinite dimensional integrals, but they can be approximated by finite dimensional integrals, and then they are exactly of the form that I showed before.
Perfect. Thank you very much.